All right, there. So, some reason it's behaving kind of funny, but. All right, there we go. Okay, so that's hard to see, but so far, remember, just to review very quickly, we talked first about concentrations of carriers, electrons, holes in different situations. Then we used that to calculate currents. Okay, that's where we are now. We're trying to calculate what the current is. Last class we talked about what's called the drift current. So if you apply a voltage, how do the carriers move and what kind of current is produced? Today we're going to talk about what's called the diffusion current. Okay, which is basically if you have a concentration difference of carriers, they diffuse. And of course, that gives rise to current as well. We need to calculate both these currents for both types of carriers, holes and electrons, to account for all the current in the semiconductor. So we need to understand each of these parts carefully. Okay. So we're going to start where we stopped last time, which had to do actually with the scattering. Okay. So we were talking about still mobility. So this is still to deal with the drift current. So you apply voltage, electron moves. What is the velocity as a function of the applied electric field? It is described by mobility, right? Mu. Okay. Remember the units are centimeters square per volt second and so on. And this is plotted in log scale. So the question here is, how does mobility change with temperature? Remember we talked about how concentration changes with temperature, how the material changes from extrinsic to intrinsic, and so on and so forth, right? Remember that? We also need to understand how mobility changes with temperature. Clearly there are you can see there are two things here. The horizontal axis is temperature in log scale. The vertical axis is the mobility in log scale. Okay? So let's think about what happens at high temperature. At very high temperature, the lattice atoms are moving around very fast. So one would expect electrons will collide more often with these lattice atoms. Okay? So one would expect more collisions, which means that the mobility should drop. So indeed, that's exactly what happens. And qualitatively, the way to understand this, like I said, the carriers collide with the vibrating crystal lattice atoms because they're moving around because of the heat. And as temperature increases, these collisions increase in frequency, and the probability of the electron colliding with these atoms increase. And hence, of course, their velocity decreases. Remember, the collisions give rise to the deceleration. So if you recall, if you apply an electric field, the electron will, of course, get accelerated in this direction, right? But if it's in vacuum, it will just get accelerated. Nothing else happens. But because we have a lattice, electrons will collide with these lattice atoms and will decelerate. This deceleration induces a force which balances the acceleration, right? And you get a steady state velocity, which is described by the mobility. Okay? That's the picture. Now, of course, if the temperature increases, this vibrates more, which means it will collide more. Deceleration increases, which means that the velocity decreases, which means that the mobility decreases. Okay? Qualitatively is the way to understand it. Quantitatively, again, we won't derive it, but the temperature dependence goes something like that. Okay? What happens at low temperature? Okay? We know at very low temperatures, first of all, the lattice atoms don't move around much. They're pretty much fixed. Okay? At very low temperatures, of course, the issue is that the electrons themselves won't be moving around much because they don't have much thermal energy. So any collisions that do happen tend to be more significant. Okay? So from that perspective, you can see that the velocity should also decrease at low temperature. Or in other words, the mobility should also decrease. So indeed, that's the way to think about it. So at low temperatures, what's important is primarily scattering from crystal defects. So if there are charged donor atoms or acceptor atoms or crystal defects like no atom present and so on and so forth, you get or ionized impurities. So your charges, they will scatter from these charges. At very low temperatures, it's not the motion that's important, but it's just the charge interactions that are important. So in that case, and due to the fact that at low temperatures the electrons and holes move very slowly, any collision is much more important. Okay, so you see the effect is much more significant. So again, you see a drop in the mobility. So what this says is that you have to be careful when you design a device, that it needs to if you want a particular operating range of temperature, you need to account for this. And typically you want somewhere there where the mobility is fairly constant. You don't want the mobility to be changing. Because remember, if the mobility changes, the frequency, basically the speed with which the electron can go from one side to the other side of a transistor changes, which means that the speed of the switching of a transistor changes, which means that your clock speed of your computer and so on can change, which is very bad. Okay, so it has very important implications later on in terms of devices. Keep that in mind. Again, think about this from a very qualitative perspective. I want you to understand the physics. Okay. The other few things we need to understand about mobility are that in the approximation that we will consider, the scattering events are unrelated. They're basically random. The fact that an electron scattered with this atom versus it will scatter with another atom downstream is completely unrelated because they're totally random processes, which means that we can define mobility for each different kind of scattering phenomena. Okay, so scattering with ions, scattering with atoms, scattering with other electrons, all these things can contribute differently to mobility, which means that if you have different scattering events that you can analyze separately, you can calculate the mobilities and add them up. And they add up in a harmonic fashion. Okay? Again, this is less important, and when you do actual examples, it will make more sense. But keep in mind that the scattering events are completely random. So we can model them such that you can add the mobilities independently. Okay? It'll come into play later on, so don't need to worry too much about it. The next important impact, the parameter that impacts mobility, is the concentration of donors or acceptors, impurities. So as we saw in our temperature graph, impurity scattering tends to be important at low temperatures, not at very high temperatures. But even at room temperature, if you increase the impurity concentration, there will be more scattering that happens. That's common sense, right? If you have more impurities in your lattice, of course, electrons will have higher probability of colliding with them, scattering from them. Okay? Indeed, that's what will happen, so which is shown in these graphs. So the vertical axis, again, is mobility. The horizontal axis is impurity concentration. So in this case, I forget. Let's see. So this is for silicon, and this could be a donor concentration or acceptor concentration. So you can see the two graphs. One is mu n, which is the electron mobility, and mu p, which is the hole mobility. Okay. So as the concentration of the impurity increases, the mobility falls because there's more collisions happening. And it's the same for germanium, and it's the same for gallium arsenide. Okay. By the way, if you recall from last class, do you remember why there is such a big difference in mobility of the electron and the hole for gallium arsenide? Anyone? We mentioned this last class. Orders of magnitude different. Any thoughts on that? No? Okay. Remember, the mobility in a given material depends on the curvature of the band. It depends on the effective mass. We talked about this specifically. For gallium arsenide, the curvature is very large for electrons, which means that the effective mass is very low. Mobility is high. The opposite for holes. Okay. You can have huge differences, of course. That's what you see. These differences between the different materials comes from the band structure, clearly. Right? Okay. Keep that in mind. You should be able to make those sorts of connections. Okay. And these are log scale, so these are very big differences, as you can see. Okay. So I mean, let me just reiterate this point. So you see the mobility. If you increase the concentration of impurities, let's say you dope the silicon from 10 raised to 14 per centimeter cube, say to 10 raised to 19 per centimeter cube. That's 5 orders, and that's very typical. Okay, that's not very huge or anything like that. It's very standard. You can see the mobility drops by several orders of magnitude. Okay, so even though you are, of course, why do you dope? Why do you add impurities? Because you want more carriers, right? You want to make it more N-type, let's say, the silicon. So you're trying to get more carriers, but at the same time, you need to be aware that the mobility is dropping several orders of magnitude as well. So you need to be careful that two things happening. You're increasing the carrier concentration, which of course can increase your current, but your mobility is dropping. So you need to find an optimum concentration that you want to work with. Okay? Because remember, mobility increases, concentration increases, current increases. That's roughly the way to think about it. But if mobility drops, current also drops. So you're trying to increase the concentration, but mobility is dropping. So you remember, there's a sweet spot where all of this should work, depending on what your device characteristics should be. Okay? And of course, you can calculate that very easily based on the equations from last week. Okay? Just drift current. Okay, so let's do a quick example problem. And I want you guys to actually discuss and do this. It's from the text. Very simple problem. So a silicon bar, 0.1 centimeters long and 100 micrometers squared cross-sectional area. Okay? Okay, the area. It's doped with 10 raised to 17 per centimeter cubed, so donor concentration. Phosphorus is a donor per centimeter cubed of phosphorus. Okay, it has an extra electron. Find the current at 300 Kelvin with 10 volt applied. Very straightforward question, right? You should be able to do this now. Temperature is 300 Kelvin, so that's room temperature. Okay, and we are just applying a voltage, just like we saw in last class, of 10 volts. Okay? Okay, I'll let you guys start. Discuss for 30 seconds with your partners. I mean, think about it yourself, discuss. I want you to actually discuss because it makes a difference when you think aloud a little bit. Then we'll work through it together. I also have to give you the mobility. So assume that you know the mobility, okay? So I'm going to give you the mobility is 700 centimeters squared per volt second. Okay, so let's start. How would we address this question first? Okay. As we apply, we are given voltage. Okay, I'm going to simplify this for your freshman class. Okay, this is basically it. No, you have voltage applied. Okay, you have some resistor here. You want to find the current. Pretty much, right? Of course, now we're diving in to understand the physics of what this is. But more or less, this is what it is. Okay, so how would we calculate the current? Oh, come on, you know this from my high school physics. How do you calculate current? Yes, so V equals IR from Ohm's law, and I is just what? V over R. Okay, pretty simple, no? V is voltage, it's given, it's 10 volts. So all we need to know is resistance. So really what it's asking is what is the resistance of the silicon. Okay? If mobility is given, by the way, the reason mobility is given is because you can, from this And from this, you can look this up in the table, basically. And I'm just giving it here. Or you can calculate it or whatever, depending, you know the equation. So if you know mobility, how do you calculate resistance? Okay, now let's think about resistance. What's resistance? Resistance is directly proportional to the length of the bar, inversely proportional to the area, multiplied by the resistivity of the material, right? Again, this you should have learned in your undergrad, freshman class or whatever, right? Longer the bar, the more resistive it is. The wider the bar, the less resistive it is, and it's just multiplied by the resistivity, right? Now, resistivity is nothing but 1 over conductivity. Okay, this you know is 0.1 centimeters. This you know, 100 micrometers squared. Sigma, you need to calculate. Okay, and if you look, sigma is related to mobility. Right? Mobility times the charge of the electron times the concentration of the electrons. We're just assuming it's mostly electrons in this case, which is a reasonable assumption because the doping is very high. Okay, the intrinsic concentration, remember, is only 10 raised to 10, so you're about 7 orders of magnitude higher. So you can make that assumption. Okay?
Wait, how did you find conductivity? I was writing stuff down.
Here, this is from last class. Conductivity is given by mobility times the charge times the number of electrons.
Okay.
Of course, you need to also, if you want to do this rigorously, you need to consider holes as well. But it is such highly doped material, you can ignore the holes. It's mostly electrons. And we are talking about drift current right now. Okay? This was from last class, so go back and review if you don't remember. Okay? So you know mobility, you know electronic charge. Again, I'm not going to give you electronic charge because you should know it's just a constant, right? 1.6 times 10 raised to minus 19 coulombs. And then it's just the concentration, which is nothing but that, right? Remember, when it's highly doped, concentration of electrons is the same as the concentration of donors. So this is that. Okay? Okay, again, I'll walk through the logic very quickly again because I want you to understand the steps. I don't care about the math, so don't worry about actually doing it. I mean, you should do it in your problem sets, but I don't care right now. So remember, you're applying a voltage to a bar of silicon. Silicon is pretty much basically just a resistor from our perspective, so we can think about it this way. When you apply Ohm's law, voltage is given. You need to know the resistance. Resistance related to the geometry of the material through conductivity and resistivity. And all you need to do is calculate conductivity. Or resistance. It's the same. They're reciprocal. Okay? And of course, conductivity is related to mobility and carrier concentration. This is what we have been focusing on for the last two days. Last two classes. Okay? So again, make sure you follow the logic. Okay? You will do many of these in the problem sets or similar kind of things, so you'll get more practice. Okay, so in this case, the current, it's about 1.12 milliamps, whatever. Okay. Okay, so far we have assumed that Ohm's law is applicable. So here, we apply this. Okay? It's not always true. So what does Ohm's law mean? If I plot current versus voltage, okay, I should get a straight line, right? Resistance is a constant, basically, which is what's plotted there. So it's field, but same thing. So if you plot the velocity of the electron, drift velocity, okay, which is related to current, centimeters per second, as a function of the applied electric field, you see an interesting behavior. Down here, you see a straight line, okay, which is basically what's called ohmic regime. The Ohm's law is applicable. But at some point, once you apply enough of a field, electrons will gain so much energy that the extra velocity that's gained from the field is lost by collisions with the lattice. And the velocity will basically saturate, which is what you see here. So no matter if you apply a higher field, the velocity does not increase anymore. And this is what's called the high field effect. We should be aware of this also. Because why? Because sometimes we need to also put a range of applicable voltages for your devices, okay, your transistors. What is the voltage that the highest voltage that's allowed? Okay. So again, to reiterate, at the low and moderate fields, Ohm's law is valid. You get a straight line. So recall, this is the equation we're plotting, right? This is basically mobility is basically the ratio of the average drift velocity of the electron divided by the applied electric field. The negative sign because they're moving in opposite direction. Applied field is this way, the electrons going that way. But mobility is always positive in this case. Okay? So it's a constant. Basically what this is saying is that at low fields, mobility is a constant. Doesn't depend on the field. At high fields, it depends on the field. Basically saturates. Okay? So mobility and conductivity doesn't depend on field strength, so it's a straight line. And at high fields, the drift velocity becomes comparable to the thermal velocity, which means that, remember, the electrons are jiggling around because of the thermal effect, and the drift velocity becomes comparable to that velocity. Then the extra energy that you apply from that the electron gains from the field goes into essentially collisions with the lattice. Okay, so more lattice collisions occur because it's moving so fast, and the velocity essentially saturates into what's called the scattering limited velocity. So we should keep this in mind as well. Now, this will be relevant, for instance, here in this example that we talked about. We first should actually, if we are to do this very rigorously, we should actually calculate the field and make sure it's in the low field regime, so we can apply Ohm's law. I just applied Ohm's law, right? Because I assumed it was low field. So what is the field here, by the way? 10 volts. How do you calculate the field, average field? You have a silicon bar, you apply 10 volts. What's the field? Say that again? Yes, but what is the field? That's correct, yeah. So it is applied field over the distance over which the voltage is applied, right? So it's 10 volts divided by 0.1 centimeters, or 100 volts per centimeter, right? So let's look at it. It's 100 volts per centimeters here. So it's low field. So you can apply Ohm's law. Of course, it depends on the material. This is silicon. But this is, again, something you should be aware of. Okay, we'll come back to this later, so don't worry too much about it. So you can see if you get to about 10,000 volts per centimeter, then you have a problem. You have to worry about high field effects. Okay? Again, understand this conceptually. Okay. Next, we are going to move into a very interesting and important topic. Okay, we're going to shift gears somewhat, still related to drift, but a new phenomena which we will introduce called the Hall effect. Now, the Hall effect was discovered even before semiconductors were well understood. This was discovered in the late 19th century. And the person who discovered it won the Nobel Prize for this, I believe. And his last name was Hall. I forget the first name. Some British physicist. Okay? So it's a very interesting phenomenon. And the reason we are studying this today is because this turns out to be the characterization tool to understand and study semiconductors. So before we dive into the physics, let's make sure we understand very clearly why we are studying this. Okay? Hall effect is useful to measure the carrier concentrations in any material. So let's say someone gives you a bar of silicon and asks you, okay, tell me what the carrier concentration is. Hall effect allows you to actually do a very simple measurement to very accurately estimate what the carrier concentration is. So it's an extremely useful tool, as you can imagine. Okay, because there's no easy way to measure carrier concentration if someone gives you a semiconductor, right? You can't count carriers. Okay? So this phenomena gives you an opportunity to do that. So let's understand what this is all about. Okay, so first before we think about it, let's imagine a silicon bar. Okay, just like we drew here. It's just a bar of silicon. It's p-type. Doesn't need to be, but let's just assume it is. Okay, for the sake of simplicity. Okay, and the directions are shown here. That's the x-axis. Along this is the direction, long direction of the bar. Z-axis is shown there, and the y-axis is shown there. Okay, straightforward so far. Then we apply a voltage, an electric field, just like we did in this example. Okay, so current flows. Okay, no problem so far. Now the new thing we do here is we apply a magnetic field. Okay, that's shown here. BZ. The magnetic field is applied orthogonal to the electric field direction. So the electric field, of course, is in the x direction. Okay, just like here, it's applied on the ends. The magnetic field is in the z direction, orthogonal to the electric field. Okay? So far, so good. Now let's think about what happens. If there's no magnetic field, remember our picture last time, the electrons just flow opposite to the field, the holes flow in along the field. So if I draw so just look at this. You apply this sort of a field, the holes are basically going to flow that way, right, along the field. Okay? So nothing strange, everything's fine. As soon as you turn on a magnetic field, what happens? The hole will experience a force. Okay, this is the so-called Lorentz force, which you should have learned in your freshman class, I think. Okay, which is given by that. Of course, this part we just saw, which is the force that the hole feels because of the electric field, is just Q times electric field. Okay, that's just electrostatic force. Okay, but the magnetic field, because it's a moving charge, induces a Lorentzian force given by that part. Okay. Now, of course, this is a vector product, so let's think about that carefully. So you have a velocity of the hole, which means it's going in that direction. You have a magnetic field pointing up. The force is B cross B. Okay, it's a vector product. Now, to do vector calculus, I mean, you should go back and review it, but the simple rule is to use the right-hand thumb rule, right? If you take your right hand, if you do V cross B, so your V, just pointing my fingers, and B, you curl it over the B, you will see a force pointed by the thumb, right? If I take V cross B, I get a force, which is essentially pointing in this direction. It's the magnetic force. Okay? And this magnitude is given by just the V times B. The direction is given by V cross B. Okay, this is just Lorentzian force from electromagnetics. You have a moving charge in an electric field, it sees a force. Okay, so what would you expect to happen is that the holes will start deflecting to the side, right? It's experiencing a force. It's supposed to go, right? So just by applying a magnetic field, you expect these holes to essentially deflect to the side. Indeed, that's what happens. Okay? So far, so good. But of course, in steady state, if the holes, by the way, if the holes deflect this way, that means there's a current this way as well. There's no applied field, right? And there is no circuit here. So you cannot actually have a steady state current. So in steady state, that current must be zero. There cannot be a net motion in this direction, which means that something must prevent this force from happening. And that something is what's called, is essentially an electrostatic field. A field gets set up. A built-in field starts building up within this material, which opposes this force. It becomes equal and opposite to this force and prevents the hole from going this way. Okay? Physically, the way this happens is very straightforward. Some of the holes initially come to the side. Once you have a few holes there, which means that you have a positive charge there relative to the other side, you set up an electric field. which opposes more holes from coming in. Right? It's as simple as that. So if you have a few holes here, that means you will end up with a field which is pointing in that direction, right? Positive charge here relative to the other side. So you get a magnetic field force which goes this way. You have an electrostatic built-in field that gets built up that prevents that force. Okay, in steady state. Okay, we'll visualize this in a second. Actually, maybe it's the right time to do it. So there's a little animation which shows what happens to some extent. This is done with electrons, but it's the same thing. Just ignore that. Ignore the sign of that battery. So you're just applying a voltage, just like this, right? No magnetic field. In this case, imagine they're holes. They're actually electrons. Do you see that? First of all, because it's going into the positive terminal of the battery. The same principle for the holes. Okay, they just flow as usual, right? Now you apply a field. Okay, so you see what happens? You get a force which pushes it up. Okay, now a few of the electrons have gone up. Then it's said because of that, those electrons will repel any further electrons coming. You see this happening. You set up a field, and it goes back to what it was doing before in steady state. And this is called the Hall effect. Okay, so so what has happened? Just by applying a field this way and a magnetic field this way, you get a field this way. A field appears this way, and that phenomenon is called the Hall effect. Okay? And it happens for any material, by the way. It doesn't have to be a semiconductor. In fact, I posted a video online which shows it for a very simple microscopic thing. Okay, so let's go back to this equation first. So what the force in the y direction is given by that. If you actually work out the components, you get QEY minus Vx Bz, and that has to be balanced by a set up electric field. Okay, a new electric field must be set up to balance this force, otherwise the holes will deflect along y, and this is so-called Hall effect. Okay, now. In other words, this force, the whole force must be 0, so Ey must be Vx times Bc. Okay, and we'll derive that in a second. Okay. So the whole voltage. So again, what has happened? You apply voltage this way, you apply magnetic field this way, you see a voltage appearing this way. Okay, and that voltage, or because of the built-in field, is called the Hall voltage, and you can calculate that Hall voltage as VAB is the field times the width of the bar, right? So if you have a field this way, and the width of the bar is W, the voltage is just the field times the width of the bar. Okay? The current, if we come back to why this is important, let's go back to what we learned last class about what the drift current is. The drift current is given by just that, right? Minus Q N Vx, where N is the carrier concentration, the concentration of electrons. Vx with these brackets is the average electron velocity, right? Now, we can relate this to the field, clearly. Electric field is given by the current divided by QP naught times Bz. Now, what is that? Because that's just the voltage, right? Voltage times the width. Okay. This, of course, okay, let me step back. Let's write this down so we can look at this together. So we know from here how the field is related to the velocity of the hole. So Ey is Vx times Bz. Okay? That just comes from the setting this force to be 0 in steady state. Now, we can substitute for average value Vx, because Jx given by So I can take this and put it there. So what do I get? Okay. In this case, holes. So I gotta do this for holes. And this becomes positive. Okay. So I put the equation for electrons, but the same thing for holes, remember? Just ignore that. Okay, so that's this. So far, so good? Okay, and this term is written as RH, JX, BZ. This is the so-called Hall constant, or Hall coefficient. Okay? It just depends on okay. Now you can see why this becomes important. Actually, we'll get to that in a second. Okay. So remember, as I told you at the very beginning, the Hall effect is important because it allows you to measure experimentally what the carrier concentration is. And it becomes obvious now. This is the carrier concentration. Okay? So let's write down what that is. P naught explicitly is 1 over Q times RH. Okay? From here. Okay? RH is what? This can be written as right from here. Okay. Now you see. Okay. Now let's think about this for a second. What are these things? Jx is a current density. It's the regular current. Easy to measure, right? You put an ammeter, you can measure it very accurately. It's coming out of the semiconductor, it's the regular current. Bz is what you apply. You put it, so you know exactly what it is. It's a magnetic field. Q, of course, is just a constant, you know that. Ey is the built-in field that appears due to the Hall effect, and you can measure that. You can measure the voltage and divide it by the width, you get the field. You can measure that very accurately. All these things can be measured or known very accurately. These are external parameters. So by measuring this, you can calculate that. Okay? So that's the beauty of the Hall effect. Is that these things can be measured accurately. Well, you know, in this case, they convert it to currents, but the same thing. Okay, you see basically. Right? In this case, basically they convert the current density to current. Current density is basically current divided by the area of cross section, so it's W times T. Come back here. This is W and this is T. The area is W times T. Right? The current density is just Ix divided by Wt. And the Hall field is essentially the voltage divided by W. Right? It's like we talked about before. The W just goes out of the equation. That's the only thing. So you get just the thickness comes in. Okay? So these things can be measured accurately. Now we can experimentally measure the Hall concentration. Okay? This is why it is extremely important. You need to really understand this because it's an important characterization tool. Of course, you can do the same thing for electrons. We did this for holes. Same thing, exact same thing happens for electrons. You have to be careful with the signs. That's all. Because the electron moves in the opposite direction. It will deflect the other way and so on and so forth. Okay, but exact same thing happens. As we saw in the animation will store electrons. Okay, this is why the Hall effect is very important. Okay, we can also measure resistance of the bar, right? That's very simple. That's just what we did here, right? You come back to this model, you know the applied voltage, you know the current because you can measure these with an ammeter and voltmeter. From Ohm's law, you know what the resistance is, V over I. Okay? From resistance, and this expression, you can compute the sigma because you know these dimensions can be measured very accurately, the length and the area and so on. You can calculate resistivity or the conductivity. Okay, now think about this. Now you can measure conductivity very accurately. You know the concentration very accurately. You can measure mobility, right? Because mobility is another very important parameter. Okay, so it's basically what it says here. We can calculate resistivity as R times area divided by L. Okay, and of course that's equal to the voltage divided by current by L over Wt. It just comes from resistance is voltage over current. Wt just goes to the bottom. The mobility can be calculated easily as sigma over q p naught. Sigma is 1 over rho, and p naught is just that. And mobility is just the Hall coefficient divided by the resistivity. Hall coefficient we know because we just measured it. Okay? Hall coefficient is that. We just measured P naught, so we know everything. So at the end of the day, the Hall effect allows you to measure the two most important parameters required to understand drift current in semiconductors, which is the carrier concentration and the mobility. Okay? There's no other easy way to measure this. That's why this is very important. Of course, you can do the same thing for the n-type material. As I said, the Hall voltage and the Hall coefficient are both negative in that case. Just because it deflects the opposite way, right? So, as you can imagine. Okay. I won't belabor the point. Let's take a quick look at an example. So again, to understand these things, I will reiterate that you should really try to do the review problems, problem sets, and so on, because that's the real way to really understand the concept. Okay? And when you do these, don't just apply the equations. Think, like I said, I don't really care about the equations. I want you to think about where they come from, like we did that particular example. So let's try to do this example along those lines. Okay, I want you to discuss now. Okay, let's read the question first. Okay, according to figure 325, I forgot what that is. Let me take a quick look. Yes, that's just the bar. Okay, that's just this thing. That's a picture of the Hall effect. So I'll show that again in a minute. Okay, consider a semiconductor bar with a width of 0.1 millimeters, thickness of 10 microns, and length of 5 millimeters. Okay, for an applied field of 10 kilogauss, and we'll say what that is in a second, in the direction shown, which is the direction here, 1 kilogauss is 10 raised to minus 5 Webers per centimeter squared. Don't worry too much about it. We'll see that. That's just the units of the magnetic field. Okay. And a current of 1 milliamp, which is what you measure, we have a voltage of minus 2 millivolts. Okay? VCD is 100 millivolts, which is the other direction. This is the built-in voltage that appears. Find the type, concentration, and mobility of the majority carrier. Okay, it's a very standard question. Okay, so I want you to discuss with your neighbors for about 30 seconds or so. Think about this. Okay, and talk to each other. Try to figure out, again, I don't care about the numbers, how you will approach the problem. Okay? Then we'll do this together. Okay. Okay. Let's get started. So how would you address this? What is the first question is what is the type of the semiconductor? Is it a P-type, N-type, intrinsic?
N
What?
type.
Why?
Because AB is negative.
What?
What? I don't know.
What did you say? I didn't hear you. Say that again.
Oh,
It's okay if you don't know. That's fine.
it's N type. I know that.
Why?
Because VAB is negative.
So what is VAB? First of all, let's try to understand what that means. It is correct. Okay. So VAB is the applied voltage. Okay. And that's a current. The voltage is negative to the current, which means that it's an electron. The majority carrier is an electron. Okay. In this case, that's VAB. It's minus 2 volts, and the current is flowing this way, so it's opposite, so the electrons. That's a simple way to answer. Okay, is that clear to everyone, first of all? Okay. Oh, actually, wait a second. AB is the other way. My mistake. Although we can say the same thing. Okay, let me say this again. Yes, go ahead.
Is there a standard way of labeling those sides? Is A?
No, you can do whatever you want. They're referring to that figure, and I messed up.
Do you always label A as positive and B negative?
No. Don't. So what I said just now is not the actual logic. Okay, let's go through this again. Why are there carrier electrons? Let's think about this. The Hall voltage that appears is negative. Not the applied field, applied voltage. The Hall voltage that appears in the material, the built-in voltage, is negative, VAB. Okay? Now think about what that means. If they are electrons, okay, and you apply voltage like this, the electrons of course will move in that direction. Sorry, the electrons will move in the opposite direction of the field. And the force on the electron would be, it's B cross B with a Q, but Q is negative for the electron, remember that? So B, right hand, so B cross B means that the force is going in, and the force will be pointing in this direction. But because of the electron charge, it's actually pointing in this direction, you get a minus. Okay, so the electrons will all move to this side. The electrons move to this side, holes on that side, you get a field pointing this way. Okay, this is the same situation as for the holes, if you recall. Okay, but of course, and that's the way you should think about it, work through the logic. But of course, the easy way is look at the Hall voltage. If the Hall voltage is negative, there are electrons. That's the easy way to say it. Okay. So in the Hall effect, the voltage that comes, the built-in voltage that you measure is negative compared to the applied voltage, then your majority carriers are electrons. Okay? And you can work it out in terms of the forces, just like we did for the holes. Okay? What's the next part? The concentration. So the concentration of the carriers is what we did here. Okay? We did here for the holes, the same thing for the electrons, right? It's the current density times the field divided by Q times EY. Okay, you know everything except EY. EY is what? It's the built-in field. So let's rewrite that equation in terms of electrons. So the whole electron concentration, we know there are electrons first. The electron concentration is given by the current density, the applied field, divided by the charge, times the field. Okay? I don't care about sign because I know this is positive anyway. It's just the concentration. So I'm going to ignore any signs. What is Jx? The current density. Anyone? Say that again, I can't hear. Yes, it's just the current divided by area, right? So the current, what is the current? It's 1 milliamp divided by area is what? 0.1 millimeters multiplied by 10 microns. Okay, that's just the current, you know that. Okay? I'm not going to calculate, doesn't matter. BZ, you already know, 10 kilogas. Q is just electronic charge, again you know. EY, so what's EY? Yes, it's the Hall voltage divided by the width of the bar. Okay, so what's the Hall voltage is minus 2 millivolts divided by the width of the bar is 0.1 millimeters. You know that. So now you know everything, you can calculate it now. Of course, just be careful that you don't get, because these two are negative, they will cancel out, right? But anyway, concentration is always positive, so you don't, and you won't make that mistake if you use some common sense. Okay? So you can calculate the whole concentration, electron concentration in this case. Last question is, what is the mobility? Now you know, if you know concentration, mobility is straightforward, right? Recall the mobility, where is it? I erased it. Mobility is just, what is it? I forgot.
Sigma over the charge times the concentration.
Okay, good. Sigma over the charge times. Okay. About sigma? Yes. So is that given? I forgot. Let's see. Sigma. So we need to know sigma. Okay, sigma is 1 over rho. That's the other part. But rho is given by R A over L. Right? Just like before, it's the exact same example as before. So resistance times the area divided by the length. Now resistance, you know why? Because you know the current and the voltage. Right? Resistance is V over I. So V is VAB, sorry, VCD, not the whole voltage, divided by the I. So this is what? 100 millivolts divided by 1 milliamp. Okay? Got it. So again, it's very important that you follow the logic, the steps on how to solve it. So there's a lot of involved steps here. I know you just saw it, so it might be a little bit abstract right now. You may not follow it. But let's very quickly review. Okay? So for the type of the semiconductor, you look at the sign of the Hall voltage. Yeah, I'm more the way. If you need to see, you can come down. Come sit here. Yes, Sam. No. So the concentration should not become negative, right? It's just a number. It's just the concentration of the carriers, right? The way you can tell from the Hall measurement whether it's N-type or P-type is just look at the sign of the Hall voltage. If the Hall voltage that appears is negative, then you know they're electrons. If the Hall voltage that appears is positive, you know they're holes. It's pretty simple. Okay? And of course, to understand why that is the case, you have to look back at the last few slides and see what happens with electrons or holes. We did it for the holes. I suggest you do it yourself for the electrons, so you understand it. Okay? So the logic again, first, to see the type, look at the sign of the Hall voltage. Second, to calculate the concentration, all you need is the field, the Hall field, right, or the Hall voltage, basically. So it's given by current, field, current density, field, charge, magnetic field, charge, and electric field. You know everything here. Okay? To calculate the mobility, you need to know resistance. If you know voltage and current, you know resistance using Ohm's law. from resistance and the geometry of the bar, you know resistivity, which is a property of the material. Then you can plug it into this equation to calculate mobility. Okay. That's the progression, the steps you need to actually solve a problem like this. And you will get a lot of practice. So it'll come to you later on. Okay? Okay. So again, I want you all to go back and do this yourself. Okay, just go back. It's in the text, but just go through it yourself. Okay, and I'll post the review problem so you'll get some practice. Okay, so let's continue on to the next topic. Okay, we're going to change gears a little bit and coming to another important phenomena. Essentially, what happens to the Fermi level at equilibrium when you have carrier concentrations of different kinds, okay? So, and this is actually quite important later on when we talk about p-n junctions and so on. So, and this is a very general, basically almost like a theorem that you can apply in a variety of situations, okay? So let's take this case. Let's take one material 1, let's say it's n-type silicon, okay? And it's placed in contact, essentially, with p-type silicon on the other side. Okay, material 2. And this we will see next week, I think, or the week after, will be a p-n junction. Okay, this is the basic device that we will study. So it's very important that we understand it right now, the basic concept. Okay? We won't go into the device details. We just want to talk about the Fermi level right now. Okay, they're in intimate contact. What the invariance of Fermi level at equilibrium means is that at equilibrium, the Fermi level must be the same for all materials in intimate contact. So if you go from one material to the next, the Fermi level cannot change. Okay, recall, what is the Fermi level? It is the energy level in a semiconductor where the probability that that energy level is occupied is 50%. Okay? Energy level above that, the probability of occupation is lower than 50%. The energy below the Fermi level, the probability of occupation is higher than 50%. That's basically it. Okay? And it has to do with the Fermi-Dirac statistics. Okay? We saw before. So let's see what this means, the invariance. Okay. So a couple of other things before I go into it. We will define that the density of states in this material is N1. Recall that's the number of states available at that energy level. And the Fermi distribution is F1. And same things N2 and F2 for material 2. Okay? So the materials are in intimate contact, which means that the electrons can move back and forth. Electrons and holes. Okay, that's basically what that means. There's no energy barrier there. But there might be energy barrier, but it's a continuous energy barrier. Right at that edge, there is no barrier. We'll come back to what that means later on, so don't worry too much. Just imagine that the electrons and holes can flow back and forth with no impediment. Okay? So what is the rate of electron flow from material 1 to 2? Okay? It depends on two things. It depends on how many electrons are available in material 1, so they can flow. And it depends on how many unoccupied energy states are available in material 2, so they can flow into it. Right? Pretty straightforward. How many are there here, and how many empty states are there on the other side? You need both, right, for this flow to happen. So that's what's shown here. So it's proportional. The electron flow rate is proportional to the filled states in material 1, which is the number of electrons available in material 1, multiplied by the empty states in material 2. The filled states in material 1 is essentially the density of states, N1, multiplied by the probability that the states are filled, F1. Okay, pretty simple. The empty states is basically the density of states at E, so this is available states, times the probability that the states are empty, which is 1 minus F2. Okay? So far, pretty straightforward. Okay. What happens the other way around? What is the rate of electron flow from material 2 to material 1? Exact same thing. It is the probability of the number of filled states in material 2 multiplied by the number of empty states in material 1. Because you need to have electrons on the other side and empty states on this side. Okay, so now it becomes N2 times F2 times N1 times 1 minus F1. Same logic. Of course, in steady state, there should be no net flow of electrons one way or the other, meaning these two rates must match each other. Okay? In steady state, there should be no current if there's no voltage applied, right? So these two states should match each other. So at equilibrium, there can be no net electron flow. The rates must be equal. So you set them equal. So that's the rate from material 1 to 2. That's the rate from 2 to 1. If you set them equal and you solve it, essentially what you get is that F1 equals F2. In other words, the Fermi-Dirac distribution on the two sides must be the same. In other words, the Fermi level on both sides must be the same. Okay? Now, this is a very general principle, if you think about it. Because we haven't made any assumptions as to what the material is. It can be germanium and silica, it can be anything. All it's saying is that as long as you're in equilibrium and you're in intimate contact, such that the energy states, the electrons can move back and forth freely, then the Fermi level across the materials must remain the same. Which is kind of a very important principle if you think about it. Because remember, the Fermi level typically depends on temperature, depends on band gap and all that stuff, right? Okay. It depends on doping. Remember we talked about the Fermi level goes closer to the conduction band, it's p-type, goes closer to the valence band, it's n-type. Well, but what it's saying here is that if you take all the two materials, n-type and p-type, and put them together, the Fermi levels have to match. Let me, to help you visualize this, let's draw the Venn diagram, at least qualitatively, okay? So this is the valence band, this is the conduction band. We'll actually come back to this, but I want you to think about this. If this is n-type material, where should I draw the Fermi level? Approximately, where should it be? It should be in between, let's say, but where? Come on, you should see. We talked about this a week ago, I think. Somewhere. Yes. Closer to the valence band, a conduction band, right? The Fermi level should be, let's say, up here. Remember? Go back and review. You will have to review all this because all the problem sets, the second problem set is all dealing with all this stuff. So, okay? So let's draw the p-type. Where should the Fermi level be for a p-type? Okay, you can say it. You know it? No? Yes, it should be closer to the valence band. Right. Okay. Now if I put these two materials next to each other, you see what happens? I dictated just now that this Fermi level have to match. Right? That's what we just proved. What does that mean? The energy levels, of course, have to be continuous. They cannot have a discontinuity like this. I will prove that later. Which means that you end up seeing something like this. Okay? And this is basically a p-n junction. This is the basis of all transistor electronics today. Okay? And we will talk about this, I think, in a week or two. I want you to understand why this principle is important, because we can use this to understand a lot of things that's going to happen. Okay? Okay, so at equilibrium, the Fermi level must be the same for all materials in intimate contact. Okay, I think I'll stop here. So, because we covered a whole bunch of math and so on, so I want you to think about this before I jump into diffusion in chapter 4. Okay. So for those of you who came in late, there were a couple of announcements.